Hi guys, welcome to Unit 13 Notes B. Today we're going to talk about fission and fusion. So first, fission. Fission was the one where the heavy nuclei was splitting into the lighter nuclei. So this splitting process would happen spontaneously for elements that are unstable. It could also happen if you bombard particles, such as neutrons, onto stable elements, then they can be induced to undergo fission because the atoms would now have the wrong proton-neutron ratio, which would cause them to become radioactive. So some things are naturally spontaneously going to decay, and some things can be convinced that they should decay. So we also have fusion, where the two nuclei, or lighter nuclei in general, are combining to form a heavier nuclei. So we have smaller particles combining to form larger particles. So this is what happens in the sun. Fission does occur on Earth in two different ways. We're going to talk about nuclear bombs, and we're going to talk about nuclear reactors, which are both fission. Fusion, on the other hand, so much crazy amounts of energy. This is what's powering the sun. So there is a difference in the amount of energy. Fusion produces a ton more energy than fission. Fission still produces way more energy than a typical exothermic reaction. So it's kind of a hierarchy here. So let's first look at fission in the use of the atomic bomb. So the nuclei for the first nuclear bomb anyway was for the uranium-235, where two isotopes would be formed, and then you've got some other neutrons being emitted. So as they go through this fission, we're going to get a chain reaction, and this idea of a chain reaction is a huge deal when we're looking at both fission and fusion, actually. So the chain reaction is going to be caused by unstable atoms producing neutrons, and those neutrons creating bigger and bigger problems, more and more neutrons, in almost an exponential function. So we have what would be a stable nuclei. If it gets bombarded by a neutron, that can then induce fission. And notice what else is being emitted. All these other neutrons. Well, neutrons are the bad guys. These neutrons that are produced are now going to go and cause fission in other atoms that were stable. So you get this multiplying factor where the chain reaction kind of gets out of control. So we can take a closer look here. We're going to look at an example where the red would be their target nuclei, the green would represent our neutrons, and you can see that it just goes, and as it's more and more neutrons are being formed, that reaction occurs faster and faster, and it gets really out of control. So let's watch that one more time. Started off with just one neutron, right? Now there's quite a few more. And then very quickly there become many, many more. So it's picking up speed as it goes through. So this is our chain reaction producing a lot of energy at once. If each of that splitting, each time the neutron comes in and makes contact with a stable nucleus, it then makes it unstable, and that's going to spontaneously decay. That's what radioactivity is all about, emitting some more neutrons. And those neutrons will then go find other things to make unstable, and this process will continue and continue and continue. One way that we can kind of control that is by using a concept known as critical mass. So critical mass is basically the minimum amount of material, fissionable material, meaning something that can be induced to decay, in order to sustain a chemical reaction. Not a chemical reaction, sorry, the chain reaction, the one that we were just looking at. So if I have not enough mass, then I'm going to prevent that chain reaction. Maybe the particles are too far apart. You're not going to get that chain reaction to continue at that exponential pace, and you're not going to be able to have this crazy out of control reaction. So the idea here is that you create areas in the bomb where you have subcritical mass, meaning there's not enough mass in either section on its own to create enough of a reaction to carry forward. But if we store it in two different pockets in the bomb, then we can kind of explode the insides of the bomb the old-fashioned way, TNT, and that's going to allow now the subcritical masses to combine. Naturally, by gravity, they would kind of fall down together, right? And then once we reach critical mass, then we can get that out of control chain reaction and get the giant nuclear explosion. So there have been two bombs, nuclear bombs in history. The first was named Little Boy, and that was the one that the United States dropped on Hiroshima, made of uranium-235. And then there was a second bomb named Fat Man, which was actually powered by plutonium. And that's the one that the United States dropped on Nagasaki. So slightly different. Here's our little boy. And then here's our fat man. So you can see where they kind of get their names from. Little boy, fat man. So the fat man had the plutonium core, and the little boy had the uranium. It's not labeled on here, but it had uranium as its power source. So those are the two bombs that have actually been dropped in historically. All right, so that's nuclear bombs, kind of a negative way to use nuclear energy. Now let's look at a positive way to use nuclear energy. Let's look at nuclear reactors. Biggest misconception I hear is that one of them is fission and the other one is fusion. That is not the difference. They're both using fission. The reactor is going to be different from a bomb because it's going to control the rate by taking some of the neutrons out of the equation. This means that my chain reaction doesn't get out of control. It is controlled by allowing only one neutron to sustain the reaction and continue on making things radioactive, whereas some of the other neutrons would be absorbed. So it's also going to use subcritical mass, which is we just talked about as another way that we can control it. Those uranium fuel rods, or fuel pins as they call them here, are going to go into something called the core. Another way that we can control the rate is by using something called control rods. Kind of an obvious name there, right? The control rod's job is to control the rate of the uranium decomposition, that chain reaction, by absorbing neutrons. So control rods absorb neutrons. If I put in more control rods, that would mean absorbing more neutrons, and that would result in a slower reaction. I'm saying this backwards. So what I just described is the second point. Putting the more control rods in is going to decrease the fission, decrease the rate. Whereas if you pull control rods out, you're going to increase the fission, meaning the chain reaction is going to pick up speed. So we can control how much energy is being produced by controlling the control rods in the core. We just don't want to get too greedy and allow this chain reaction to get too out of control, because that's how nuclear meltdowns happen. So there's a safety feature now, and this was actually a result of a very famous meltdown known as Chernobyl. The idea here is that if we drop below a certain amount of power, if, for example, the power was cut, the control rods will by default go into the core, kind of shutting down the core, as opposed to what happened in Chernobyl was not enough control rods were in, and then there wasn't enough power to put more in, whereas if that were the default, then we wouldn't have had such a problem. So the default position now is that control rods go in instead of out. Getting more safe as we go along. So we do have some nuclear reactors in the United States. They are more concentrated on the East Coast as opposed to the West Coast. That's because on the East Coast, there's a lot more water. So nuclear reactors tend to be near oceans and streams and lakes because they do use water to cool themselves. So the reactors are typically found near some kind of body of water. So they look something like this. Maybe you've seen them driving down towards San Diego. We have a big steam part, and then we have part where the actual fissionable material would be kept. So lots of crazy controls. You can see how complicated this would be. Now let's talk about how this actually translates to generating electricity. How does having a fission reaction produce electricity? So the fission's job is actually just to generate heat. It's producing a lot of energy, and that's going to make things very hot. The water is then going to need to turn into steam, but there is a catch. We wouldn't want water that's in contact with radioactive material to turn into steam. Then we'd have radioactive steam. So there's actually two separate loops. One that's coming in contact with the radioactive material. We actually call that the radioactive water loop. And then we have the non-radioactive water loop. And they come near each other in this like concrete shielding container so that the heat can be transferred, but the radiation isn't transferred. Then that second non-radioactive water loop is going to turn into steam. Well, steam rises, right? And as it rises, it's going to turn something called a turbine, which is attached to a generator. And a generator's job is to make electricity out of that rotational energy, converting that into electrical energy. So this basically boils down to heating up water. Why is this better than maybe coal power or something like that? Well, the amount of energy produced by a small amount of radioactive material is tenfold times rooms full of coal energy. The efficiency factor is insane. We get a lot of energy in order to heat up the water out of very small material. Let's take a closer look at these loops I was mentioning. So the core is pictured over here on the left, and you can see both control rods and fuel rods into the core. That radioactive water loop needs to be pressurized so it doesn't turn into gas, and needs to be pumped so it's going through a circuit. There is a concrete shielding that's around my heat exchanger, and the heat exchanger's job is to let the water transfer heat energy but block the radiation. Then we're going to have the non-radioactive water loop over here, which is being pumped around so that the steam can then come in contact with the wheels of the turbine, allowing the generator then to do its job in creating electricity. So the main idea here is that you understand there are two separate sections. One where the water is getting hot because of the radiation, and then one where the water is turning into steam to run the turbine. So let's end this with pros and cons of nuclear energy. One of the biggest advantages of nuclear energy is that steam that was coming out of the top of the factory was not smoke. It wasn't full of like a carbon footprint, like it's not producing carbon dioxide or any kind of pollution in that sense. So the steam is just pure water vapor, which can go into the water cycle and not cause any negative side effects. The other thing is its efficiency, which I've mentioned a few times now, is bar none above and beyond any other form of energy that we have come up with so far today. The other thing is it is so efficient. One could even argue that it's a renewable resource because we're not going to run out of it before the sun burns out. Like, we have enough to last a really long time. Whereas fossil fuels, on the other hand, are slated to run out not that long from today. So when we run out of the fossil fuels, what are we going to do? And one of the answers could include using nuclear energy, since it produces so much energy. There are, of course, some drawbacks. For example, after the fuel rods are done producing efficient energy, they're still not safe. In the next set of notes, we're actually going to talk about something called half-life, which is going to explain how this radioactive material will always and forever be radioactive. So the waste needs to be handled very carefully. Right now, we're putting it in something called Yucca Mountain, which could erode and break, allowing that radiation to escape. Even sites for nuclear meltdowns constantly have to be readdressed to make sure that the protective barriers that we put around them aren't eroding away, so that we're still making sure all of the radiation is contained. Another major drawback is something called thermal pollution. Now, I mentioned how some of the reactors are built next to water bodies. So say we need to cool down the reactor and we pull in a huge amount of water. The water's got a very high specific heat and it's able to absorb a lot of energy. Well, then we put that hot water back out into the ecosystem. Now the organisms that were used to 25 degrees Celsius water are now exposed to 80 degrees Celsius water. Well, that's going to kill some organisms, and that has a way of working its way up the food chain. So we want to be careful about adding extra heat into an ecosystem and possibly killing off some of the creatures that would live there. The other negative side effect or negative possibility, the con for nuclear energy, is that some people have bad intentions. So it is possible for the fuel pins themselves to become hazardous due to intentional human behavior, possibly stealing the fuel or attacking one of the nuclear reactors themselves. So that could possibly, not just by mistake, but on purpose, create meltdowns. Something else that's not on here actually is that they do, by mistake, happen to melt down, not only due to human error, but also due to environmental conditions. Like Fukushima was due to a natural event. So we want to make sure that no matter how much we think we have control, we are taking precautions, because there are some cons to nuclear energies. Of course, also some pros. So that's going to do it for fission and fusion. Unit 13 notes C, the last one we have left, is going to talk about the half-life of nuclear materials. We'll see you there.